Welcome to you students. Welcome to video class number one, labeled as Introduction to Control System. And in this video, I'll start with the definition of control system, and then again we'll be reconsidering the example which I have discussed with you in the previous introduction video, and using that I'll be explaining the difference between open loop and closed loop system. Then some of the features of the open loop and closed loop system will be discussed. Then we'll see some of the examples of real-time control system, and you will be able to uh, classify each system as open loop or closed loop. And finally, we'll be dealing with the control system model, and which is an important topic as far as the analysis of the system is concerned. Okay, now for the textbook details will be sent to you through the Google Classroom, and I don't think you can access the library right now, but you may just check for the online edition of those things. If it is available, you can just refer. Okay, anyway, for the meantime, you may just write down all those things which has been told in a separate notebook, and it will have to be submitted at the end of the course for the evaluation. Okay, so have a nice day and enjoy this course. Okay, here we go. So let's see the meaning of this control. What is the meaning of control? Control refers to regulate or command or direct, and while system refers to an arrangement of some physical components. Okay, so this is just the word meaning of this control as well as systems. Now what we are going to do to understand control system, we combine these two. Now what if when you combine these two, you will see that you can define this control system as what? How do you define the control system? You can define this control system as an arrangement of the physical components to control itself or some other system. Okay, to some other system. So basically the meaning of this is the system is meant to control. That's why the name control system. So here is, you have again two tanks, two cases, where the first tank, you are pumping water into the tank, and the water rises and it comes to this level. At this level, so the controlling parameter here is the level. Okay, the water level. But there is no, in this case, there is no mechanism to calculate or the measure the level. The level is to be controlled, but that level cannot be controlled, and once it reaches this nozzle, water will be flowing outside, resulting in overflow of water. Okay, so this overflow of water gives an indication for the manual control of this pump, uh, thereby switching off this pump. Okay. Now in the second case, here also you have the water at the bottom. Okay, as the pump is switched on, this water rises, it covers this, and you can see, assume that you have two sensors kept, one at the bottom, other at the top of the tank. Okay, now it rises, and once it touches this sensor, what happens is sensor will produce a output voltage, right? Okay, and if you can use this output voltage to switching circuit which is capable of switching off the pump, imagine that scenario. So you're using the signal that comes from the sensor, and you're taking the signals that comes from the two sensors, and using these two information, you can either switch on and switch off the pump. That is, now what happens after, so at this point when it reaches here, because of this signal, this pump switches off. Now what happens is, when the water is consumed, the level decreases, and as it reaches the bottom, this will again give another indication to this. So asking this switching circuit to switch on the pump. So this is purely automatic, and not only that, here what you are finding is you are actually controlling, here also you are controlling the water level, that is your output, right? But this water level or the control action, so what type of control action is happening here? Both the cases, the control action is switching off the pump. The control action depends on the water level, while in this case control action is not depending on the water level, but only once the water level reaches this, the overflow makes a person to switch off. So that's a difference. So since there is a physical connection from the output side to the input side, we'll call this as the feedback. And here in this case you can see there is no such feedback. So that means you can from this you can have the classification of these two control system. These two are control system. Why these two are called as control system? Because in the two systems it controls. It is an arrangement of physical components to control itself or to some other. So it's controlling something. It's controlling the water level, but that control action is not depending on this water level, right? While the control action that takes place here depends on the water level which is to be controlled. Okay, so since there is no direct relationship or the connection between the output and the input, this is open, right? So this system we call as the open loop control system, while this one we call as the closed loop control system. Okay, it's called as a closed loop control system. Okay, now we have seen that the control action. Okay, what is the control action here? The control action is to turn off the pump. Okay, now this turning of the pump in this case is not depending on the level. Okay, no measurement is taken for the level, while in this case the output or the level is periodically measured, okay, and is combined with something, right? So it must be, I mean, there must be some associated circuit with this, and thereby it induces a control action. So based on the control action, based on how this control action depends on the variable which is to be controlled, we can classify this as open loop and closed loop control system. So you can have a definition like this. You may just have a look at this. Open loop control system is a control system is one in which the control action is independent of output. That means in this example, the control action, that is the level, the control action is the switching of the pump is totally independent of the output. Only the overflow makes a person to switch off the pump. It is not the level. Now, while in the closed loop control system, it is one in which the control action is dependent on the output. Now, whether to switch on or switch off depends on what? Depends on the level. Okay, so that's the difference. Okay. Okay. Hope you understood the definition of open loop control system and closed loop control system. And from this example, I think it's very clear that in an open loop control system, you are not measuring the output. As in the first case, you are not measuring the water level, while in the second type, that's in the closed loop system, where the output is frequently measured. Okay, periodically it is measured. Now let's move on to the next portion, which is the features of open loop control system. And the following are the two important features of open loop control system. Number one, its ability to perform accurately depends on calibration. I'll explain what is calibration. Calibration, it refers to the re-establishment of input-output relationship to desired system. That is, say, for example, let's come back to this example. This is the example of an open loop control system. Now, what's the problem with this system? The problem with this system is the accuracy. That means at the correct point, you may not be able to switch off the motor. That means there can be a loss of water, because in almost every cases of our real-time homely affairs, we usually switch off the pump when we hear the sound of the water overflowing from the tank, right? So such a control you cannot call as a accurate control. No, you can make it controllable by setting, say, when the tank is empty, so you can calculate the time that it takes just before it overflows by once watching. And you can and once when the tank is empty, you can switch on the pump by setting a timer or looking at your watch. And you can more or less when it reaches reaches the time which you have already recorded, then you can switch off the pump. Okay, so that is called as calibration. You can think you can think in that line, that is re-establishment of input-output relationship to the desired system accuracy. So beforehand we know that it will take this much time, and if you can set a timer, and now as it reaches that time, you can switch off the pump, and not only that, you can ensure that the tank gets filled by the water, but as well as the pump is switched off before the outflow of water. Okay, so that's the only way by which you can make it accurate. So one of the problems of this open loop system is it's not accurate, but if that system is suitably calibrated, then you can have an accurate result. Now, can you think of a situation where this calibration, the system can lose its calibration? I'll give you an example. Now, you're actually pumping it from your well, right? Now, in your summer season, what happens is the water level in the well will also decrease. Now, once it decreases, the pump may not be pumping the water in the exact volume as it was before. So obviously this will take too much time. Okay, right? So what happens is if you switch off the pump as by your timer, there can be a chance that you cannot always ensure that the tank is full, because it may take too much time, so that the tank may be well below the highest mark. Okay, so that's one scenario where the system can be inaccurate, or an external parameter can cause the inaccuracy of the system. That is, when the pump slows down, it can disrupt the system. Okay, so those disturbances, or those causes, can be called as an external disturbance. Okay, so that's a problem. And another feature of this is, it is not troubled by the problem of instability. We know that in your circuit classes, you might have studied about oscillators. Now, oscillation. Now, I have already explained in the introduction video regarding the stability. Now, what's the meaning of stability? That is to maintain. By stability, it refers to maintain the output to its consistent desired value. Okay. Now, what will happen to this case? That is, if this is the desired value, and if the output is fluctuating like this, or is oscillating like this, then you will say that the system is unstable. So when a system oscillates, you have studied in your circuits, the oscillation is the result of a feedback. Now, in an open loop system, you cannot find any feedback, because the reason is because there is no feedback. There is no feedback. Because there is no feedback, no chance of this open loop system to go into an unstable state. So that's in any way, that's an advantage of an open loop system. Okay, but the problem is, its accuracy depends on the calibration. If by any means the calibration, the system loses its calibration, then its accuracy is worstly affected. Okay. Okay, now let's move on to the features of closed loop system. Anyway, we know that closed loop system is a system with feedback. So all the advantages of a feedback system, as well as the drawbacks of a system, of a feedback system, will be the advantages and drawbacks of a closed loop system. So the number one, it is the increased accuracy. Now we have just seen that in an open loop system like this. Okay, in an open loop system like this, the system accuracy is affected by any change in the input side. So as I have mentioned earlier, that if for some reason, if the pumping force decreases, then there can be inaccuracy in the system. Now, what happens in this case? In this case, if suppose the pump slows down, anyway, this pump is not going to switch off when the water level reaches the midway of this tank, as in this case, because even if it it will only switch off when the water level reaches at this point. So that means the system is accurate because this is not affected by the change in the input parameters, as we see in this case, while this is affected. Now, second point is the tendency to oscillate, right? Now, as I've mentioned earlier, that oscillation is a result of feedback. So since this closed loop control system is having a feedback, there is always a tendency of the system to oscillate, and that's a drawback of the oscillate. Now, even if it is a drawback, we must understand that there are a lot of advantages of this closed loop system, for the closed loop system, when you compare with the open loop system. So even if there is a chance of the system to go to instability, all the other advantages makes it more attractive than open loop system. Okay, now so you may be wondering, then what about the instability that is caused? And that's what we will be studying in this course. There is methods by which we can analyze the stability of a system, and if found unstable, there are some techniques by which we can make a unstable system to a stable system. All that will be dealt in the later modules. Okay, now the third one is the reduced sensitivity of the ratio of output to input variations in system parameters. So the meaning of this statement is sometimes the system parameters will change. So sometimes the system variables, the, the, the parameters, the various parameters inside system, for example, in electronic circuits, you can see that as sometimes inherently the inside the temperature can increase, and because of the temperature increase there can be change in the output. So that sensitivity of the output to these type of system parameters gets reduced. So that's an advantage. That means for the system to be accurate, this should be very less sensitive to the change in output to the input. Okay, now the next one is the reduced effects of non-linearities, and we know that this system is physical components, and these components which we use may be usually it may be non-linear, and the impact of non-linearity will also affect the output. But because of this feedback, this feedback will reduce the error caused due to non-linearities. Okay, you don't have to bother about this. How will it come? We'll be explaining when we go into the details of this closed loop system. Okay, now next is the reduced effects of external disturbance. So as I have mentioned in this example, see, when the pump slows down, that's an external disturbance to the overall system, so that it has lost its calibration. Now if even such scenario happens here, because of this feedback, what will happen is it nullifies the error caused due to that change in the parameters or the external disturbance. Now next is the increased bandwidth. That refers to how well the system responds to input variations. That is, say, if the system, this control, the system will be having very high bandwidth. The will be the bandwidth increases refers to the fact that the system is capable of controlling a very high input variation. So that's the what is the primary role of a control system. Even if the input changes, input varies for some reasons, the output has to be maintained or output has to be controlled. Okay. Okay. Now let's see some examples of control system, some real-time examples. Number one is an electric switch. Now we know that an electric switch is having two positions, a normal switch that is on and off. Say for example, if you're using a switch to control a fan, you have only two options there, that is either to on or to off, and which can be considered as the simplest of the control system. Simplest of the control system. Okay. Another example is a thermostatically controlled heater used for regulating the temperature of a room. So in this case, what happens is this system will always check the temperature of the room, and if it goes below the set value, so anyway there will be a set value. I will be explaining what it is, the reference value. So based on that reference value, it will it will try to maintain the temperature of the room. So since it measures the output of this particular control system, this one is a closed loop system. This one is a closed loop system. Okay. So this is exactly what happens in a air conditioning system as well. we set the temperature, and whenever nowadays the compressors are always it won't be always on. It will be turned off when the temperature is maintained within the desired or the set value. Okay, now when it if it goes high, only then the compressor again starts, and thus saving electricity in the modern modern air conditioning systems. Now, another control system is a human temperature control system, which is the perspiration system. You know, as the temperature, outside temperature increases, we sweat, and the sweat is actually a control action done by the human body to maintain the coolness of the body, or to maintain the temperature inside the body. So it perspires, and that evaporation in the form of sweat will be inducing some cooling inside the body. So that is again a control system. Okay. Okay, the next example is a control system consisting of a person driving an automobile. This control system has uh, both and manufactured and biological components. Hope you understood what I meant. This I'll explain. Manufactured means the automobile. So you have the steering, you have gear, you have accelerator, you have clutch as well as brake to control the vehicle, and to aid the driving. You also need the biological component of the human body. That is, you need eyes, hand, legs, as well as ears to. Okay, so for the smooth driving. So this is actually a culmination of both biological and the artificial component that makes up a control system. Okay. Okay, another example is an automatic washing machine, and you may be much aware of that, which does the rinsing work, then after that washing and drying based on a timer. So this can be considered as an open loop system, and you may be wondering why this is called as an open loop control system, since it is set it to be automatic. Yes, of course, many of the automatic systems are open loop control system. So I'm going to recollect the definition of an open loop control system. Open loop control system is one which the control action is independent of the output, or you are not measuring the output. As far as a washing machine is concerned, the output is not washing or drying or anything else. It is the quality of washing. So in this automatic washing machine, there is no provision for checking the quality of washing. Okay, so all these process, that is rinsing, washing and drying, all these process happens within a set time, and we believe that after that set time that clothes are properly washed, but there is no mechanism to check the quality of washing. Now suppose, imagine that in this automatic washing machine, if there would have been a system to check the quality of washing, and if it is not properly done, it can be re-washed again without any sort of timers, then the same system may be called as a closed loop control system. Another example is an airplane controlled by an autopilot system. So once if it is autopilot system, then it becomes a closed loop control system. Okay, now you can read many textbooks to find out different types of control system. Not only that, you can just have a lot of real-time examples. There are many examples that you encounter daily in your life. So these are all the examples of control system. Now, why I listed these examples is I just want to make a point very clear. So in all these control system, something is controlled, right? Some variable is controlled. So for example, in the electric switch, we know the flow of electricity is controlled, right? In a thermostatic controlled heater, temperature is controlled. Here again the temperature is controlled in this. Here the driving direction, the speed, all these things have been controlled in the automobile person driving. In an automatic washing machine, there also the processes like rinsing, washing, drying, everything is controlled. So anyway, for any control system, there will be some parameters or some variables which has to be controlled, and um, so uh, it has to be controlled based on some reference. Say for example, when you set a timer, I'm putting the timer when I put the timer say for 5 minutes, I mean the control system will be working, or the washing machine will be working for that 5 minutes. So the 5 minutes is a reference point. So, for example, in the case of a thermostatic, I mean, in the case of an air conditioned, as I mentioned, I have set the temperature to be 25 degrees Celsius. Now, what happens? The compressor will be active till it achieves the temperature 24 degrees Celsius. Now, as it achieves the 24 degrees Celsius, then the compressor will be turned off automatically, and the air conditioning system will be checking again and again the temperature of the room. Once it goes above a set level, so there also you need a reference. A set level, again the compressor is turned on to maintain the temperature back. Okay, so this is how a control system works. And control system, when you observe the control system, you can identify whether the system is an open loop system or a closed loop control system. Okay. Okay, after having an understanding about the examples of control system, let's see something about the control system model. Okay, now by model it refers to the representation of the system, representation of various components of the components of control system. Okay, this is very important. So the representation of the components of a control system. Now the model can be there are three different models that we use in a are extensively used in the study of control system. They are, number one is a mathematical model. I'll explain what it is. Mathematical model. Then you have the block diagram model, and number three is the SFG. Okay, SFG. I'll tell you what it is. Okay, now let's move on to the mathematical model. Okay, now model is just a representation of the components of the control system. Okay, now this mathematical model, say for example, you know that a control system, any system, it will be having an input as well as an output. So as far as a control system is concerned, it will be having an input which is your desired or the set value. As I mentioned in the case of a air condition, 24 degrees Celsius is your input that you have given to the system, and the output varies, and output will be measured periodically. So that means any system, so I'll just explain. Say for example, I'm just considering it as a block with an input as well as an output. So this input and output will be having a mathematical relation. Okay, mathematical relation. And as you have studied in signals and systems, any system with an input and output can be represented by mathematical functions or mathematical relations which relates the output to. So you might have studied something like this. I have taught you, say y of t is equal to some transformation of x of t, right? So there can be some linear equations or like this, or there can be some differential equation. Okay, so this is the time domain representation mathematical model. So similarly, under this you can have a frequency domain model as well. So in the frequency domain model, you will be defining what is called as a transfer function model. Okay, can you recollect what is transfer function model? Yes, I have taught you. So for example, consider this output as y of t and this as x of t. What is transfer function? Transfer function is the Laplace transform of y of t to the Laplace transform of x of t with the initial condition is equal to 0. So by transforming using Laplace transform, you are converting this time domain signal to frequency domain. So transfer function model is a frequency domain representation, while differentiation and linear equations are time domain model. So hope you understood what a model is. It is actually a kind of representation. In this mathematical model, here you will be representing the or relating the output and input by some mathematical functions that may be in time domain or in frequency domain. Okay, now next is the block diagram model. In block diagram model, what it does is it is just a pictorial representation of the relationship between input and output. I will explain what it is. Say for example, you have considered, I've given you an example of an automobile, a person driving an automobile. So I told you that is a control system consisting of artificial components as well as biological components. Okay, so each components can be considered as a block and they are related to each other, right? So the relationship can be pictorially represented. So such a representation we call as, so you can have different blocks. Each block represents different components of that, and each can be related like this. Say sometimes some components will be used in the forward path, and some may be in the feedback path. Okay, so okay, something like this. So that means this is just a pictorial representation of the various components, and it gives you how they are interconnected to each other. So now, provided when you combine this block diagram as well as the mathematical model, especially the transfer function model, you can arrive at various type of analysis, which I will be explaining later. Then finally you have SFG. SFG stands for signal flow graph. Okay, signal flow graph. It is basically just as the block diagram. Okay, and it will be represented as lines which actually gives a path of the, see here, suppose consider this as a system. Okay, here you will be having an input and your output. Now there can be different ways by which the input goes in different ways and finally reaches the output. So SFG, signal flow graph, gives you an idea how the signal travels and comes at the output side. Okay, so it is just a representation of lines, and that it doesn't have any sort of blocks as in block diagram. It's exactly similar to block diagram, and it is basically used for easy way of finding out the transfer function from a block diagram. Okay, now okay, now I told you we have just seen the different types of models, and why do we need to study this model? The model is for analysis of the system. Hmm? For the easy analysis of a system, we need models. So as I mentioned, we'll be utilizing the transfer function model from the mathematical side, and combining this transfer function and the block diagram, you can find out the overall transfer function of a system. Say, for example, I told you each component can be represented by the block diagram, and each component may be having a transfer function of that. Now, by suitably connecting it, you can find out the effective transfer function of that system. Now, if you have the transfer function, that is a mathematical equation, and we have a lot of tools to perform various types of analysis on such systems. Thereby, we can check, especially the stability. Why? Because as we have seen earlier, that closed loop control system is the effective control system by any means in comparison to an open loop transfer as a control system. The only dominant drawback is its instability, or there is a chance of the system to go into an unstable side. So for that you require analysis of the system. So by analyzing, you can see that if some restrictions is made suitably, then that system can be prevented in going to unstable state. Okay. And you may not be understanding it too much. You will be I'll be explaining all these things when during the course. Okay, fine.